Hello everyone, my name is Vuong. I'm student at the Ocean Engineering Department, Pukyong National University. My advisor is Professor Yun-Tae. Today I will present a research topic related to monitoring technology of landslide and adaptive flow. The title of research is Deep Learning and Vision-Based Integrated Early Detection System for landslide crack propagation and adaptive flow movement. This slide shows content of my presentation. I will talk about the detection system using CNN for landslide crack propagation and adaptive flow movement. A proposed method to calculate the crack dimension and front adaptive flow velocity dataset preparation and a metric to evaluate performance of detection system. Finally, I will present the result and conclusion. Crack and adaptive flow monitoring system. Figure 1 shows traditional landslide crack and adaptive flow monitoring system using sensor. On-job using sensor is very reliable. So there are several disadvantages, including high cost of installation and maintenance, monitoring with restricted area, and difficulty in processing data in the field. So I want to propose a potential method using camera detection model for crack propagation using CNN. This figure shows a flowchart of crack detection and dimension calculation using CNN and image projection IPT. The first we need to prepare image and label crack image for training model. After that, image projection techniques basic framework to model CNN to calculate the length and the width of crack. To identify crack in this research, I apply 4 different segmentation models: UNES model, APN model, LINES, and DeepLab model. For adaptive flow detection model, I apply a deep CNN based on Yongso-ro framework to detect adaptive flow motion, and figure 9 shows network architecture of Yongso-ro for detection adaptive flow motion. Measurement the crack dimension. To calculate the length and the width of cracks, firstly we need to find center line of cracks on image. Then a square grid scan on the image to divide the crack center line into small center line segments. In the square grid, we determine the coordinate of the start point and the end point of small crack, and the total length of the crack is the sum of length of each crack center line segment using equation 1, and the average width of the crack is the average of the crack segment width using equation 2, and equation 3 transform the pixel unit to millimeter in work coordinates. Dataset preparation. We build a dataset for crack and adaptive flow detection system. Image and video of crack and adaptive flow collected from experiment, small volume test, medium and large volume test. Also, we collect image from the field. The correct dataset include 510 images, and that below extract from 12 video with around 6,000 frames, including the below object. Evaluation metric: IOU, precision, recall, and advanced score, and AP are used to evaluate the performance of segmentation model and finger 12. So the label is an predictive result to define true positive for positive and for negative prediction of detection system. Now I present several results of detection system in this table, and this finger performance of crack and flow detection model on testing data sets using different CNN model, UNES, PNS, LINNES, and YOLO version 4 is similar, but we can see the accuracy of CNN model for detection crack and rapid flow is very high, around 90%, and detection model using CNN is higher than traditional methods with advanced score just 55%. And this video shows result of propagation on that one, and this finger shows correct dimension over time of that one. The model can calculate the width, the length, and the area of correct over time. And here result of tattoo correct dimension over time. And this video shows the result of rapid motion using CNN model on a small volume test, large volume test, and case study. We can see the model can detect rapid flow motion successfully with high accuracy. Estimate velocity of rapid flow motion finger shifting. So velocity of front rapid flow on small volume test, and comparison between calculated velocity and measured velocity. And here, so velocity of rapid flow on large volume on two tests. When we can see there is a good agreement between calculated velocity and measured velocity in two experiments. the table show the comparison between calculated velocity and real velocity. The errors of probability methods is still around 13%, and a very high accuracy is difficult to obtain because the accuracy of calculation depends on the accuracy of detection. However, for the purpose of monitoring rapid flow and landslide, some errors can be acceptable. Finally, I will talk about conclusion of my research. The Chinese segmentation model successfully detected landslide crack propagation and rapid flow motion. The F1 score on a testing dataset ranges from 88 to 90%, and a video-based framework for calculating the graph propagation and front velocity of rapid flow using image projection is proposed. The result shows that the graph dimension and front velocity of rapid flow obtained through image projection were in good agreement with measured value. Error range 1.2 to 15.8%, corresponding to an accuracy of 84.2 to 98.8%. The speak of the proposed Sinan model achieve approximately 39 fps. So the proposed Sinan model has a high accuracy and fast processing speed, thus it can be applied to real-time detection and warning system. That are my presentation. If you any question, please send email to me. Thank you for your watching.